start off on just talking about queuing theory as kind of an introductory class, class on the topic of queuing theory. And the idea is basically like this. If you have a queue, and this will be the schematic that's most textbooks will use, we'll have some kind of a server, something that handles work coming in. And then the things that need work to be done queue up behind it. This could be a cashier at a supermarket, and these are the people online. This could be a processor in a computer system, and these are processes sitting in the ready queue. And the one that's at the server is the one that's in the running state. But the theory would end up being exactly the same. So some of the notation will be, it's popular to use the Greek letter lambda to mean, when you're studying a queue like this, the rate that's coming into the queue. Like 2 per second or something like that. Then we need to know the speed of the processor, or the cashier at the supermarket. At what speed can they get customers satisfied, done, and leave the system? So mu ends up being the Greek letter that's popularly used for the rate at which the server can service. T ends up being the mean service time for each arrival. So the mean service time would be the reciprocal. If it can do 3 per second, then it's 1/3 of a second per person, or per process. Another interesting thing we'd like to keep track of is what percentage of the time is this server in use. So we could have a queue where it's being used 70% of the time, and that would be pretty good. It would be great if we can get it up to 100%, because in an operating system sense, every process has to do all of its processing before it can finish. So if one process is running and then goes off to a disk drive, we'll let another one in. And then the processor is still working. But if it ever gets to the point where everything is waiting for something and nothing can run, now we have this processor that's just sitting there not processing anything. So we'd like to figure out what percentage of the time the server is running, and try to manipulate a parameter so that it gets close to 100%. It can't go over 100, obviously. So as close to 100% is what we'd like to do. Other things is we might want to know what is the mean number of customers in the system, like at any given time. If something's running and one is in the running state and 2 are in the ready state, then the total is 3. We might want to analyze how many are in the queue at a time. The response time for any system would be the time from when you came in until the time you're done. That would be the response time, or turnaround time. The throughput of a system is the amount of work it can get through per time. So if it can do 4 jobs per minute, that's its throughput. What we'll be doing a little bit later is we're going to take queues like this and say the output of one queue is the input of another queue. So for example, in operating systems, you could have a process that's running. It's running for a while, and then it asks for a resource that's not available, so it gets moved to a queue, but there's other things in front of that one. So we have to calculate how long does that queue take to run. And then once that's done, it might come back and feed back into here. So we're going to end up having like a network of queues where the output of one server goes into another queue, and then that one could wrap around to here. A bottleneck device ends up being, we could have a network of queues running with processes bouncing around from queue to queue, and the one where the server gets as close to 100, or the one that's where it's going to hit 100%, is the point at which that queue is considered saturated. So if you think about this, suppose the amount of work coming into a queuing system is more than the rate at which it can get out. What would happen? Not only theoretically, but what would happen in actuality? If we had a queue. Does anyone, just an idea, it's an intuition thing, but if the amount of work coming in, the rate at which work coming in, couldn't be processed fast enough, what would eventually happen to the queue? Yeah?
Overflow?
It'll what?
Overflow.
Yeah, I mean, yeah, it'll like build off to infinity. It would be like if more people were coming into the supermarket than the cashier can handle, theoretically there'll be infinitely many customers not being satisfied. So when we network a bunch of queues together, if things are bouncing around, whichever one of those queues where the server gets to 100% use, that's it. It can't the whole system can't handle any more because one of the queuing systems hit its maximum utilization, and that queuing system would be the bottleneck. And then once the bottleneck hits 100%, we really can't let more processes in because that queue would then theoretically build up to infinity, and then nothing would get done. So once the bottleneck system reaches 100% utilization, that's it. Our system can't take any more. So when we analyze a queuing system, we're going to use this notation. This is called Kendall notation. And we're going to say, we're going to have the probability distribution for the arriving, the arrival distribution. The second one could be the probability distribution for the service time. The third one could be the number of servers. The fourth one could be the capacity of the queue. Just the last example, it was an infinite queue, but we could have a capacity on the queue. Then n would end up being the number of customers in the system. We could have an open system where they could keep coming in from the outside world, or we could have a closed system and we say there's only 10 processes bouncing around. And then Z would be the queuing discipline, like first come, first serve, but there could be other queuing disciplines. So for example, if we had a queue that was, we call it A/B/C, for example, what we're doing is we're saying not only do we have an arrival rate, which we're going to use lambda to be the arrival rate, but the distribution at which they come in. So, have you guys taken a probability class? So, you know how like you could have a completely random distribution, like maybe sometimes called a Poisson distribution. Something happens at a rate of 1 per second, but when the next event from the previous one is completely unrelated. You could also have what's the other extreme, which is a deterministic event. So you could have one comes exactly every second as an arrival. So they both have an average of 1 per second, but one of them comes every second and the other one comes totally random with an average of 1 per second. So just because we know the rate, 1 per second or 10 per second, we still need more information about how the distance between each one is. So this would be, you know, the distance between the arrivals, the distribution for the service time too. We could have a service time where, like for example, a processor, a lot of times it runs for a fixed amount of time and then kicks somebody out. So every time something goes into the processor, we could say it runs for a fixed amount of time and runs out. So that might be a deterministic service time, but things that are processes that arrive to the queue kind of come in randomly. So we could end up having something like a Markov distribution of where they come in, and then maybe a deterministic distribution of when they go out. And then there's all different types of, if you remember from your probability class, the different types of arrival times. And we'll cover some of those in future examples. So just for example of using this notation, suppose we have a system like this. In this case, our queue has exactly 4 seats in it. So it's not like an infinite queue. It's 4 seats. We have 3 servers. So you can kind of think of this as 3 cashiers at a supermarket. And then we have a finite number. This is a closed system. So new jobs or new processes aren't coming in from the outside. It's a closed system. And let's say, hypothetically, the amount of time they spend here is what we're calling Markovian, meaning they have a Poisson distribution between them. So they could go into this queue at a Markovian distribution, but then let's say the servers take the same exact amount of time every time. So maybe that's a deterministic service time. So we could say the arrival are Markovian, the distribution of the service times are deterministic. There are 3 servers. The queue has 4 seats in it. It's a closed system with a total of 12 processes going around and around. And when they arrive at the queue, they are processed in a first come, first serve. We could later do things like in the queue, we could say, we could have priorities, like high priority ones get pushed to the front and low priority gets pushed to the back. There are other things besides first come, first serve, but first come, first serve is like the intuitive one. And if you leave this out, it's assumed it's first come, first serve. It's kind of like the default. And if you leave any of the other ones out, the 12, if you left that out, it's assumed it's an open system. Anybody can come in from the outside, so it's not a fixed number. The fourth, if you leave out the number of seats, by default it's considered an infinite queue. So if we called a queuing system, one of the most common ones we'll follow is the one that's MM1, meaning an infinite queue, one server, and there's a rate it's coming in, but the inter-arrival times between the rates are random, and the service time is also random. Okay, then there's a famous result called Little's Law, and some textbooks refer to it as Little's result, and it's kind of an intuitive result about arrivals into a process. So once again, we have lambda is our arrival rate. W of the queue is the mean time a process spends sitting in the queue. The number of items in the queue could be n sub q. And then we can do the same thing for the whole system, the wait time and the number in our system. And Little's result, the Little's law, is basically a formula that says the number in the system equals the rate into the system times the wait time. So hopefully this is an intuitive example. But if we have 10 people walk into a supermarket every minute, and on average they stay there for 30 minutes, then at a random point in time, how many people are in the supermarket? So I'm just hoping like the intuition is, so it's a rate of 10 per minute. So you might think, well, maybe there's 10, but that would be true if they stayed for 1 minute. If they stayed for 2 minutes, then there'd be on average 20 people there, and so on. And if on average they stayed for 30 minutes, then it would be 10 times 30, which would be 300 people on average. Now, if they came in scheduled, like let's say every minute exactly, what's it, 10 people? 10 people come in exactly at the beginning of every minute, and 10 people leave at exactly at the end of every minute. Then there might be only 10 people in at a time. But if they kind of can come in and stay random amounts of time, some people can stay an hour, some people leave after 2 minutes, but on average they stay for 30 minutes. Then this is how many people would be in the system on average. And the principle applies to the whole system, which is the queue and the processor. And if we wanted to just focus on the queue, the same principle applies to the queue. Okay, so take a look at this MM1 queue. So we left out a lot of, in that Kendall notation, we left out a lot of stuff. So the defaults are first, it's going to be first come, first serve. The queue size is going to be infinite. The inter-arrival times are Markovian. The service time distribution is Markovian. One is for one server. It's an open system, so there's no number in the system. And so let's say we consider an arrival rate, lambda of 1 per second, and a service time of mu of 1 per second. So let's just think of some interesting questions. What is the utilization, which is the Greek letter rho, of the server? Another interesting question might be, what would be the mean time you're in the system? And maybe what is the mean time that you're in the queue? So first of all, just from a kind of, let's get some intuition going, or maybe kind of think about some bad intuition we don't want to get used to. If the rate into the system is one per second, and this thing can get the processes served at a rate of 1 per second. So let's say, one person's coming up per second to a cash register, and the cash register can, well, 1 per second is kind of quick. But the cashier can get the people out at a rate of 1 per second. How big would the queue be? And just like give an intuitive guess.
So it's coming in at 1 per second.
Right.
And it takes 1 second to process it.
Yeah, the processor or the cashier, whatever you want to think of it as, can move at a speed of 1 per second. If you give it no work, it obviously does no work, but if you gave it like tons of work, it can get the work done at 1 per second.
So on average, there's going to be like 1 in the queue,
One?
or 1 being processed.
Okay, well, let's say, okay, so let's do the example of a queue that is DD1, meaning a deterministic arrival time, like it's perfectly scheduled. And when when something arrives, it will take exactly the same amount of time every time. In that case, at time equals 0, one arrives and starts being served. At time equals 1, the first one leaves as the second one arrives. So it never really gets into the queue, it jumps right into the server. And this would go on all day. So if it was a DD1 system, then there would always be one process in the server and nothing ever in the queue, because it's perfectly scheduled. Now suppose it's the other extreme, where it's MM1. So the arrival rates, they're coming in at a rate of 1 per second, but they could really, there's a total randomness to the time between arrivals. We could get 3 in 1 second, then we could wait 10 seconds and have nothing, but on average it's 1 per second. And the same thing is true with the server. Would that circumstance make it different? Now you can see there's going to be times where things will be queuing up if they come in bunches. Or if the server spent a really long time for one customer and then a really quick time for another one, while it was spending a long time, the queue might build up. So you can see the difference that even though the rate, how many come in per second and how many can get done per second, the distribution between the events actually will affect the queue. So let's see, we'll be right here. Intuition might lead you to believe that since the arrivals are 1 per second, and the time is 1 per second, therefore every arrival is served in exactly 1 second, and the previous customer leaves when the new one comes in. So you might think that the queue is of size 0. But if you think about it, it really depends on these letters up here. Could cause the queue to increase in size and decrease in size. But what about the utilization? If we take into account that at some times there'll be some things in the queue and other times there won't because of the randomness of the arrivals and the completions, would the row, the percentage of time that the server is in use, obviously it can never go above 100%, so it's somewhere between 0 and 100. Could it ever go, would you think it might go less than 50%, less than 100%? Do you think it might, there might be some times when it's not being used? And there's kind of two answers for this. When the system first starts off, you might have a scenario where it's not being used. Like maybe the first customer comes in and it gets done immediately, and then there's a little wait and it's sitting there doing nothing, and then maybe a second, a third, and a fourth come in, and now the queue starts to build up. And the queue might build up to like 3 or 4, then go back down to 0, then build up to 3 or 4 and go back down to 0. But once it's out at the steady state, it should eventually get to the point where it's running at 100%. It's just that it can't, it couldn't get the work out fast enough, so the stuff will be queued up. And there might be little areas where, for a fraction of a second, it's not being used. But it'll be 100% or extremely close to 100% over a long period of time. So the utilization ends up being, we could think of a formula now as the rate in divided by the rate out. And that would be independent of the input distribution and output distribution. So for example, if we had a rate of 1 per second coming in, and this thing can handle like 2 per second, it's like twice as fast, then this thing will be in use about 50% of the time. If 1 comes in per second and it can move at a speed of getting 2 out per second, this will be in use half the time, and half the time it'll be sitting and waiting. Okay. So then what we want to do a little later on down the road is we want to start taking inputs from different areas and running them into the same queue. So I just want to work out a little intuition here, but this could be an MD3 system, so the 3 means 3 servers. So if we had, for some reason, 2 different inputs coming into the same queue, what would be the rate into the queue? So hopefully this is a pretty simple intuition. But if one source that was sending inputs into a queue was coming in at a rate of 2 per second, and another source was sending processes into the same queue at a rate of 1 per second, then from the point of this queue, how many are coming in? It'd be the 2 added together, right? So basically we're just taking all the input sources and adding them together. So let's see, the question, what is the average utilization of the server? Okay, the average utilization of the server, we said, was the rate in divided by the rate out. So we got to figure out the rate in first. The rate in is these 2 added together. So the rate into the queue is lambda 1 plus lambda 2, which is 2 per second plus 1 per second equals 3 per second. The speed at which the servers run is 1/4. So what that means is it can do, the rate is 1/4 of a job per second. Okay, so mu is 4. Oh, wait a minute, this should be, mu is 4. This should be, this should actually be, this is the reciprocal of the rate. So this should be, it can process 4 jobs per second, which means they each actually take 1/4 of a second. This should be a different variable, meaning the reciprocal. You know, that should be, probably X is the most common one. But anyway, we could do 4 jobs per second on each of the 3 processors, which really means we have the ability, this system together has the ability to get 12 jobs per second done. And we'd have to somehow, you know, have some kind of traffic cop here saying, you know, who's next, and distribute the jobs out. Assuming that process doesn't take up any time, that instantly, as soon as one of these becomes available, we grab what's on the front of the queue and move it there. As long as that's the case, we don't lose any time to that, we have the ability to handle 12 processes per second with our serving system. So 3 are coming in per second and 12 are going out per second. So on average, each one of these servers will be in use 25% of the time. And 75% of the time, they'll just be, you know, sitting there waiting for work to come in. And like I said, what we're doing is when we start networking things together, we obviously cannot physically make any server go above 100% utilization. That will always be the cap. So let's say we had an example where this box is supposed to be a processor. I don't know. You guys ever use the tool Visio to draw pictures? Microsoft Visio. But anyway, they have icons for different things, and this is the icon for a processor. It's like this is probably like 20 years old, but it looks like the old computer towers, which have everything, including the processor and the disk drive in it. So, but anyway, so if you get used to that, this is the processor, and this is the disk drive. So suppose we're coming into the processor, and obviously inside the processor is a queue. Things are queuing up inside the processor. And something runs on the processor for a while, and one of 2 things will happen. Either it runs, so this is a pretty simple example. It will either run to completion. So in this case, there's no timeouts. It either runs to completion and leaves the system. So anytime a process enters into this queue, there's a 50% chance it will run to completion and leave the system. And there's a 50% chance it will run for a little while and then need a page from the disk drive. They'll say, oh, I'm stuck. I need a page in memory. It's not here. I got to go out to the disk drive, bring it in, and then once it comes back in, then I need to start running again. So 50% of the time it'll go out to the disk drive, and then the disk drive will bring the page back in, so the process will then start up again. Okay, So, in this system, we now have kind of two queuing systems. One which its output, a percentage of the time will go into another queuing system and a percentage of the time it will leave. So if we wanted to know on average, a question like this, on average, how long would it take for a process that's coming into our system to leave? What things would we have to calculate and add up? So you know what I mean by the question? What we're saying is, in this case, a process could come in here, sit in this queue for a while, then run on the processor for a while, and maybe it's done, or maybe it's not done. Maybe it'll go then sit on this queue for a while, get served by this disk drive for a while, then come back and start all over again. And the question we're going to try to answer is, what's the turnaround time? From the time you enter our system till the time you leave. Because we want to know on average, how long does a process take to finish? Like I said, this is a very almost oversimplified example. But if we wanted to do that, what would we have to calculate and then add up? Or how would you calculate it? Yeah.
You can find the average runtime of each operation in the process.
The average time it takes to get through here, from here to here?
Yeah.
Okay.
And then you just, I guess, divide that by 2, or multiply it by 2. That's how long it should take.
So let's just say hypothetically it takes on average 2 seconds to get through here, and the disk drive is slow, it takes 8 seconds to get through here.
Oh, yeah. Right back to that.
So would it be 10? Would it be 1 visit to this queue plus 1 visit to... So in other words, just like in English, what are we looking for? We want to know how many times, do you visit this queue? Because it's not as simple as you just visit it once and you're done. Yeah?
Okay, so if it only goes through the processor, it'll just leave 50%
Right.
of the time?
Right.
But then 50% of the time goes through the disk drive and then goes back to the processor.
And starts all over again.
Oh, that makes sense.
Like as if nothing happened. So that'll take up a certain amount of time, and then you have to actually start over again. So it's an interesting question, and it's not, don't try to think of a real process running on an operating system doing this. This is, a real one wouldn't do this. A real picture would be more like you hit the processor, many times you run and then time out, so you go right back into the processor queue. Sometimes you'll go out to a disk drive, sometimes you'll get put on a semaphore queue. That would be more realistic. So we're just trying to put an example together that's not very realistic, just so we can follow it. So what we want to do is we want to ask ourselves, how many times on average do we even enter this queue? Then we want to ask ourselves, how much time do we spend at this queue per visit? Add that up, or multiply that. Let's say on average we visit this 4 times, and it takes 2 seconds each. Well, we're going to spend 8 seconds on average here. And then let's say we visit this queue less often, but maybe it takes more time. We'll calculate how many times on average do we hit this queue, and then add them all together. So for example, if the numbers came out, we visit this thing 4 times for 2 seconds each. We're going to spend 8 seconds here. And if we visit this 1 time for 12 seconds, we'll spend on average 12 seconds each. So it'd be 8 plus 12, the whole thing would be 20 seconds. So it's how many times do we visit each queue, times how much time do we on average spend there, and then add up all the queues we visit and how many times we visit them. So that's why we want to know, we want to be able to come up with a number. How many are in the queue in front of us? How many are, well, one will be in service at the time. So when we get put at the end of the queue, how long will it take us to get to the front of the queue? So we know how long we spend per visit at each queuing station. Yeah?
Okay, so you can make like an algebra equation.
Yeah, it ends up being it's a coefficient, how many times we hit the queue, time at the queue, add it all up. So yeah, it's a pretty simple algebra equation, but we want to figure out how many times So how would you answer this question? This is kind of you might recognize this question from your probability class. But if you come into this queue, how many times would you expect to visit the processor on average? Have you ever seen this question? You might have seen this with a coin in your probability class. But if you come into this processor, how many times are you going to visit it? You're going to definitely visit it once because you always start off hitting the processor. 50% of the time you'll visit it once and you'll be done. So half the time you're going to visit it once. And the other half you're going to visit it how many times? One, at least two, and possibly more, right? Yeah?
Instead of trying to think of it like that, you could also, so you know that the runtime, 50% of the time the runtime is the processor time. And 50% of the time you know it's the processor time plus the disk drive.
Oh, that's not bad.
Plus the average runtime, I guess, wouldn't it?
Well, it was 50% of the time it's one pass of the processor.
Yeah.
And the other 50, it's processor plus disk
Plus an average runtime.
plus the time it takes, assuming you're starting all over again. Okay. Yeah, okay. That's a good way to think of it. But if we wanted to just, and that's kind of what we're doing here. So we're kind of saying, you're taking the, you would take that number and then add up the time at each of these and multiply that by however many times that number comes out. So we're kind of doing the same thing. If we wanted to calculate how many times do we expect to hit this processor, it's the comparable probability question is, if you have a coin that has a 50-50 chance of heads or tails, how many times would you have to flip it until you get the first heads? So the answer is, half the time it's going to happen on the first try. And half the time it will not happen on the first try, and then you have to start over. Doesn't mean it's going to happen on the second try. So it would be like half the time it will be the first try, and 25% of the time it'll be the second try, and then 12.5% of the time will be on the third try, and 6.25%, and so on. But what does that all average out to? So you could add up that series, 1 plus a half plus a quarter plus an eighth plus a 16th, add that whole thing up, what does that add up to? So that's one way you could do it with an infinite series, and that would add up to 2. But another way of thinking it is you could just do and use expected values. So we could say the question is, what is the expected number of visits to the disk drive? And what is the expected number of visits to the CPU? So the disk drive, I think I got these backwards. Oh no, sorry. No. Okay. The expected number to the disk drive would be half the time, for this picture, how many times do we go to the disk drive? Half the time it will be 0. And half the time it will be 1 plus you're starting all over again. So we can just numerically say the expected number of visits will be E. Half the time it's going to be 1 plus E, which is how many times you'd hit it, assuming you're starting over. So the number of visits to the disk drive would be half of 1 plus whatever E is. So now it's inductive. So now E is equal to 1/2 plus E over 1/2, and then if we subtract the E over a half on each side, we have a half and E equals a half. So E equals 1. And if we did the same type of computation on the disk drive, the CPU, how many times do we expect to go to the CPU? It's a slightly different equation. We're going to definitely hit it once, for sure. And we're picking this up from the picture. We're going to hit it once, and then half the time we're going to start completely over again. So what does that add up to, the expected number of times? The expected number of times, whatever that is equal to 1 plus half the time we're going to hit it all over again. So E is equal to 1 plus half of E. We subtract a half of E from each, we have E equals a half. 1/2 E equals 1, so E equals 2. So what we're saying here is, on average, a process entering this system will hit the CPU on average 2 times. And what that really means, half the time it's going to hit it once, a quarter of the time it's going to hit it twice, an eighth of the time it's going to hit it 3 times, a 16th of the time it's going to hit 4 times, and so on. But on average, it will hit this twice. And then, doing the same kind of math, on average, we will hit the disk drive 1 time. And if you think about it, half the time we hit the CPU, half the time we hit the disk drive. So we actually could have calculated the CPU and then just taken half of that number, and that's the number of times we'd hit the disk drive. So what we're going to do is we're going to ask ourselves, on average, how many times do we hit each queuing system? We hit this one twice, we hit this one 1 time. Now we want to calculate how much time do we spend each visit for here. Multiply that by 2. How much time do we spend for each visit here? Multiply that by 1, and then add them all up, and we've added up the whole queuing system. So we know how many times we hit each queue, and now, we're not at the point yet where we can figure out how much time do we spend at each visit of the queue. So let's just look at another system. Let's say we have, this is from an older textbook, this is terminals. You could think of these in this example, these were 18 people sitting at a terminal, and every once in a while they'd hit enter and send something into our system. And then our system it's bouncing around in some queues and then eventually comes back. So this ends up being a closed system, and the average person is thinking for, on average, 18 seconds. So someone's monitoring this system and says, I notice the average person thinks for 18 seconds. And then sends something into our queuing system. So in our system, I'm now giving, just to have a different notation, I'm now saying instead of this being lambda, instead of this being mu, I'm taking the reciprocal and saying it's 0.01. So the time it takes to service something is 0.01 seconds, which means it operates at a rate of, it could do 100 per second. So just stating it a different way. So now something comes into our CPU, 40% of the time it will go out to disk drive 1, get some page to come in from memory, and then go back to our processing queue. 50% of the time it will go to disk 2 and then come back to our system. And 10% of the time it will finish. And what it means by finish, it'll come back to the person and they'll see their answer, and then they'll go back to thinking for 18 seconds. And then they'll send in another process into our system. So if we wanted to calculate how many visits do we do at each of these systems, it's the same as the calculation before. It would end up being, well, let me just cover this thing kind of intuitively. Every time you come into the CPU, 10% of the time you're done, and 90% of the time, 40% plus 50%, get merged together and start over again. So it would be like that E equals 1 plus 0.9E. 0.9% of the time you start over again. So equals 1 plus 0.9E would come out to be equals 10. The expected number of visits to the CPU. Every time something comes out of here, it's expected to generate 10 visits to the CPU, because 90% of the time it starts over again, 10% of the time it finishes. So if you do the same computation, you realize that everything coming out of this system gets multiplied, gets re-entered into the queue on average 10 times. So once we know what that is, we could take 40% of it and we know what the input into this queue is, because this queue feeds this queue directly. There's nothing else coming into this queue. This has only one input. So if we know the rate into this one, we take 40% of it and we know the rate into this one. If we know the rate into this one, we take 50% of it and we know the rate into this. And then we want to know how much time is spent at each queue. So whatever the rate is into our overall system, let's say we don't, in this example, we don't know what that is. It's the rate coming out of the terminals. The rate into the CPU is going to be 10 times that. And then the service rate of that is it can do 0.01 per second, so 10 times 0.01. We can have the percentage of time that the CPU is in use is 1/10 of whatever the rate into the system is. So again, these are more like well, this is kind of a quasi-theoretical example. We have some concrete numbers and then we have the rate into the overall system. So the utilization, the percentage of time that disk drive 1 is running is 4 times the rate coming out of the terminals times the service rate of disk drive 1. So basically, whatever the rate is that jobs are being sent into our system, 0.352 times that number is the percentage of time that disk drive 1 is in operation. So disk drive 1, the percentage of time this is doing something would be that number. So whatever in this queue, the queue sometimes might be empty and the disk drive might be sitting idle, and sometimes it'll be working. But the percentage of time that it is in use is going to be 0.352 times the rate that's going into the system. If more work goes into the system, the rate would go up. If less work started coming in, the rate would drop. And then the utilization, the percentage of time disk drive 2 is running, it's 5 or half of the rate into the CPU, so it's 5 times the rate coming into the CPU is the rate going into disk drive 2. And its speed, let me double check this. Yeah, its speed is 0.015. So this is a slower, this is what? This is the rate, the time it takes to service one job. So this is a slower disk drive than this one. So it's kind of like we have a fast disk drive and a slow disk drive. And maybe our operating system has smaller pages on the one disk drive and bigger pages on the other. That's why one's faster or slower than the other. So anyway, the utilization, the percentage of time that disk drive 2 is running would be the time into the system divided by the time out of the system. So it would be 0.075, whatever the rate is into our overall system. So at this point, even though we don't know the rate into our overall system, if we knew this number, let's say, so for example, let's say the rate coming out of all our people sending in processes was 1 per second. If it was 1 per second, then the rate, 1 per second. The utilization of the CPU would be 1/10 times 1. The utilization, so this would be, the CPU would be in operation 10% of the time. The disk 1 would be in operation 35% of the time. And disk 2 would be in operation 0.075% of the time. If we went to 2, all of the, a rate of 2 per second, all of these rates would double. Right? So the question is, what's the maximum capacity? What is the most our system could handle? I keep going the wrong way. What is the most our system can handle? So suppose we have 3 queuing systems, and what did we say is the maximum utilization anyone can have? Otherwise, the queue is going to grow off to infinity. It's 100%, right? Once any one of our devices, it's the processor on it is operating at 100%. That's it. We can't add more jobs into the system. Because then that queue, out of all 3 of those devices, that queue would grow it to infinity if we started sending processes in at a faster rate. So our overall system, our overall queuing system can handle at a maximum whatever it takes to make the device that gets up to 100% the fastest. As soon as one hits 100%, that's it. We can't add any more. So that's going to be called, okay, so in this case, because disk drive 1 is the one that will get to 100% the quickest, that device is called the bottleneck device. And then the question is, how much work would we have to give it so that it hits 100%? And that's it. We can't add more work to this system. So then what is the saturation point? We can say, well, we spend 18 seconds thinking, and then 10 seconds at the CPU, 4 at disk drive 1, 5 at disk drive 2. This would end up being the total response time. This is how much time it would take to respond. And then if we take the total response time and divide it by the amount of time at the bottleneck device, we end up getting a calculation that we could have 52.63 jobs in this system. Once we go above that, the bottleneck device, that queue will start growing to infinity. So we really couldn't handle more than that. And just, what's this example different? Oh, this is kind of like an example we did a little bit earlier, but suppose a process was running, and it runs. If it has a page fault, we go out to the disk drive and we come back in, and if the, this is now a queuing system from the point of view of every instruction you run. Either the page is in memory or it's not in memory. We have to go out and get it. So whatever our hit ratio, that means we're going to keep doing this if the page is in memory, and if we miss and we have to go out to the disk drive to get it, that's what our miss ratio is, and then we go back to the processor and run again. So we want in an analysis like this, we want the bottleneck device to be the CPU. The reason we want the bottleneck to be the CPU is our goal in managing our operating system is so that the CPU is as close to 100% as we can. We don't want the CPU sitting idle while everything's queuing up on a disk drive. So this is kind of a theoretical model of the processor and CPU. So we want the CPU to be the bottleneck device. So what's the maximum miss ratio for the processes in our system that allow us to get to the bottleneck of, have the CPU be the bottleneck? So the role of the CPU is lambda into the CPU divided by surface rate of the CPU, which equals small t. We're saying small t is the surface rate of the CPU, and big T is the amount of time spent at the disk drive. So small t is the time spent at each visit of the CPU. So that's the small t and big T. And then the CPU will be the bottleneck if small t, the amount of time it takes to process an instruction out of memory, times the rate into the CPU, is greater than or equal to big T times the miss ratio of the CPU. So what we want is the ratio of small t to big T to equal to be greater than or equal to the miss ratio. So what does that end up meaning? Maybe I'll give a concrete example. Suppose the time to process an instruction that is in memory is 1 millisecond. And the time to process an instruction that you have to go out to the disk drive, copy the page in, and then run it is 1 second. So this ratio, 1 divided by 1,000, this would be 1,000. The miss ratio would have to be greater than 1,000. I'm sorry, the miss ratio would have to be less than 1,000. So if those were the times for your system, to process something out of memory is 1 millisecond, and to get a page out of disk drive and then process the instruction is 1 second, we have to manage our operating system so that the miss ratio never goes above 1 divided by 1,000. If it goes above that, then the bottleneck would become the disk drive. So as our operating system is managing, we know the speed of our processor, we know the speed of our disk drive. We want to manage our processes hit and miss ratio. We want to increase the size of the cache or decrease the size of the cache so that the ratio of the time coming to process out of memory and the time to process out of the disk, we want the miss ratio to never go above that ratio. So what that's basically saying is when the operating system starts giving page frames out to a process, oh, we'll give it 3 frames for this one, 5 frames for that one. We want to make sure we give enough frames that the miss ratio never violates this. Otherwise, it's not to our advantage to let more processes into the system. Does that make sense? That we want to let as many we want to let as many processes into our system as long as the scenario where the CPU is sitting idle never happens. And we could let so many in that they all get clogged up on the disk drive, and then we've actually let too many in. So there'll come a point where letting processes in is good, but we'll hit a point where if we start letting more in, each one's going to be slowing down the other ones, and it defeats the purpose of letting more in. Okay.